Hello, everyone. Welcome to CPE 517-WS Digital and Computer System Architecture. This is part 2 of lecture 7. We use software techniques to improve the instruction level parallelism. Assuming we have this code snippet, adding a scalar to a vector. See here, for I equals to 1000, when I is larger than 0, we do I equals I subtract by 1, and we're adding a scalar s to every entry xi and write it back to xi. So let's first translate this into machine code or assembly code. And assuming we have the following latencies, that is floating point operation using the result from another floating point ALU operation, the latency would be 4 cycles. The stars would be 3 cycles in between. If the floating point operation uses the result from a store, then I'm sorry. So the floating point operation produces the result for another floating point. The star is a 3. The floating operation producing result for store, it will be 2 star. Floating point operation providing instructions for branch instruction, the star would be 1 cycle. Load double, assuming the branch prediction is always correct, and load double for floating point, the star would be 1, and load double for store double would be 0, no star, and integer operation for integer operation would be no star. Okay. So here's the translation of the code. We have the load of the xi and put it in f0. It's a loading a floating point. Then we do addition of xi and s, assuming f2 is s, and put it in f4. Then we store the value of the result, the updated xi, back to xi, right? So this is, and then we subtract, since it's the double floating point, so we subtract the pointer I by 8 to slide into next. It's double word basically to next xi. Well, before we go to next xi, we have to do a comparison. See if Ri is equal to 0. If it is, then we exit. If it is not, then we go back to loop and do the execution again. Okay, I think this is clear. And this is the snapshot of the last table we explained. So in this example, we have the load producing the results to add. So let's refer to the latency table here. Load producing result to add. So there's a 1 star. So there's a 1 star here. And then we do addition. So for floating point operation producing result for store, there is 2 stars. So we have 2 stars here. And then floating point operation providing result for branch instruction. So there's a 1 star here, right? So we have 1 star here. Assuming we're starting from cycle 0, cycle 1, then we have 1 star, and then we do addition. We have 2 stars before the store, and then we do, there's no dependency from store to addition, assume there's no structure hazard and no branch hazard. Okay, then we go to we not assume there's no branch hazard because we only consider the per iteration cycle. So the hazard after the branch is not considered here. So we have stall before the branch. So in total, I have 9 cycles per iteration. Okay. So how could we, improve the performance. We can see the addition of the R1, like computing 7, is not depending upon any output, right? So maybe we can move this instruction 7 earlier. Since R1 is later used, so then we can probably do register renaming, something like this, right? So what we do is we have load R1 and then we immediately do subtraction. Right? Then we do addition. Well, the store is still counting on the output of add. So what we do is we still have 2 stars here. Afterwards, we see previously we simply store it back, right? So we use the register R1 as the memory address and 0 as the offset to store, like the same as what we did here. But before, because we subtracted R1 by 8 at cycle 2, then we actually have to add back this 8 because we have to write to the same xi, right? So this reduces stall from 2 cycles, 4 cycles to 2 cycles. Okay, so then we have 7 clock cycles per iteration. So finally, we finished the minimizing the stall by moving the adder. See here? Yeah, I did a little bit of adjustment, so we have context. So this is a prior slide, right? We say we move this one to here, right? This is where we move, basically. Just so after we move the adder of R1 from the 7th cycle to the 2nd cycle, then we see a lot of benefits, right? So we see we got the star here being filled by this adder, and also the star between the adder and the BNEZ branch not equal. This instruction also being gone. So we saved 2 cycles. So right now we only have 2 stars in the middle. Well, actually, if you take a deep look, you say, okay, this is useful, this is useful, this is useful. So in 7 cycles, we have 3 cycles useful. And then 4 cycles are either the branch overhead, right, or the stars. Okay, so for like reducing the branch overhead, like this B in Q is branch overhead, and this is also branch overhead, right? So reducing these 2 branch overhead, we can do loop and rolling, right? Well, what is loop and rolling? Loop and rolling basically tries to unroll the loop so that in one iteration, you not only execute one instance of the loop, you execute several. For instance, let's say here, every loop, instead of we finish 1 cycle, right? We finish 4 cycles. So 1 cycle, 4 iterations, right? 4 iteration, and then we change the I and the for loop, right? Well, clearly you have some confusions. For example, usually we don't know the upper bound of the loop. Then that's hard. Suppose it's n. What we should do is we should unroll the loop to make k copies of the body. Instead of a single unroll loop, we generate a pair of consecutive loops, right? First, we execute n mod k times so that it's the same as the original loop. And then afterwards, the second loop is the unrolled loop. For instance, let's see. I want to unroll it by 4 times. If I have 104, sorry, this is not a good example, 103 iterations. So what I do is I first do the typical for loop, I equals to, let's say, 1000. So what I do is I do for I equals to 1003, I is larger than 100. I subtract to the, this is the original loop. And then what I do is for I equals to 100, I is larger than 0, I equals I subtract 4. Then I do this unrolled loop by 25 times, right? So that's why what do we say by first execute the body, the original loop for the remainder times, and then we execute the evenly divisible iterations by unrolling. Since I is typically large, the remainder could be small, right? So the majority of the time gonna spend on an unrolled loop. Okay, coming here, so we have unrolled loop. Why do we do unrolling, loop unrolling? We want to reduce we want to reduce the overhead of the looping, right? So this is the overhead. So by doing this, we unroll it 4 times. So this this many extra overhead becomes 3 cycles, is divided by 4. And then these are 6 cycles, right? So we need 6 cycles. So we reduce the cycle time from 7 cycles, okay, to not 6, actually 9 cycles, right? Nine cycles. Wait, let me do a little bit edit. It's actually this one. Right. So here you go. So what do we do here is we duplicate this to 4 copies. Okay. And then the overhead of this is evenly shared, amortized by 4 cycles. So that's why we have 24 plus 3 divided by 4. So that is 6.75 cycles, right? Okay, this is say loop unrolling, by purely unrolling loops, we get a better performance than this kind of, do very sophisticated structuring, right? We structure the adder to here. Oh, not this one. All right, so moving this one to here. So we got sophisticated changes, but the cycle is only 7. But here, by do a simple loop unrolling, our cycle time becomes 6.75. Well, our question is, can we rewrite the loop to further minimize the stalls? The answer is yes. How do we do that? It's like this. From the left side, we have this load, add, store, load, add, store, load, add, store, right? So can we put load together so that the stalls from this load to this add is, this bubbles is filled by the follow-up stalls. And then the second one, for the second load, right? So the second load, the bubble is filled by these 3 instructions. So etc. We can always say the bubbles are filled. And then for the adder, before the branch instruction, we can actually get it done earlier, right? Here. Right. We change it to D. We can actually still do add, subtract 32, right? So we can do this earlier than this stop, right? So then all the cycles, all the stalls are gone, and total time becomes 14 cycles divided by 4. That's 3.5. This is a huge reduction comparing to 6.75 or 7 or 9. So 5 loop unrolling decisions. We have to understand how one instruction depends upon another and how the instructions can be changed or reordered given the dependencies. We want to determine whether loop unrolling is useful by finding out that loop iterations were independent. Like this loop is sort of independent from the finishment of the prior iteration, right? We're going to discuss this later. And using different registers to avoid unnecessary constraints, we eliminated the extra test and branch instructions where the overhead is amortized across iterations. We determined that load and store in an unrolled loop can be interchanged. We schedule the code to preserve any dependencies needed to yield the same results. Okay, so can we use 15 minutes to discuss what's the potential limitations or drawbacks faced by loop unrolling?